Okay, so this week we are moving on to section 8.4. Remember, we're in the chapter on data analysis or statistics. So last class or last week we talked about how to measure data in different ways. We can measure by finding the mean, the median, and the mode. Those are measures of central tendency that measure the center or the middle of a set of data. We also talked about measures of variation like range and standard deviation that measure the range of a set of data. Well, today we're going to take what we already know about studying data a step further, and we're going to talk about a specific type of set of data called a normal distribution. Remember, the word distribution just means it's how the data is spread out in your data set. It's where the data values lie in your data set is a distribution. And a normal distribution is a specific type of way that the data is organized in a data set. The cool thing about this lesson is that it has a lot of real world applications to it. For those of you thinking about going into the health or the medical field, lots of real world applications. And in fact, some of you guys may already have learned about normal distributions in your health classes. If you've taken one of your health occupations classes, you may already be familiar with some of this because it is actually used in the real world all of the time. I'm going to start with the notes like I usually do. This lesson this week is also going to be especially important, guys, that you're following along in the book. So, because there's a lot of graphs to look at and things like that, and I'm not going to have time to put every single picture of every graph on this little board in front of you. So, it's really going to be important that you're kind of following along with me in your book. It'll help things to go a little bit faster. I won't have to draw every single picture on the board because you can just be looking at it in your book. So if you don't have your book in front of you, please grab it. If you are using the e-textbook, you could maybe pull it up on a laptop or something and be kind of following along with me on your laptop or something. I don't know how you guys are doing this, if you're watching it on your phones or if you're watching it on your laptops. But if you can have the book in front of you as we go along, it's going to be very helpful, and it'll help me to be able to go through this lesson a little bit quicker that way also. Starting with the notes though. So the notes were both on the webpage and I also emailed them to you. Let's start by just kind of reading through that. So it starts by giving you a definition of a normal distribution. A normal distribution is a set of data that vary predictably from the mean. Many common statistics, such as human height and weight, tend to have a normal distribution about their mean. So let's stop right there. Very predictably. That means that a normal distribution is a set of data that we can predict how it's going to work. We can predict the way that the data values are going to be organized, the way that they're going to work, the way that they're going to read. And the way that they are predictable is that they're predictable as they vary from the mean. In other words, they're centered around the mean in a predictable pattern. There is a pattern to the data values, and if there's a pattern to the data values, it means that we can make predictions about how those data values are going to work. A lot of basic human statistics, such as height, weight, head circumference, chest circumference, and things like that, are what we call normally distributed. And in fact, some of you guys your pediatricians might still do this when you go to your pediatrician. If they don't anymore, they for sure did it when you were younger. Some of you guys might remember when you go to your pediatrician, they do all kinds of measurements, right? They measure your height, they measure your weight. For younger children, they measure head circumference. There's a reason why they do that every time you go in. And that is because they know that certain human statistics, human data like that, there's going to be a predictable pattern to it. And what they're looking for is they're looking to make sure that you're still fitting in that pattern, that your measurements are fitting within a predictable normal range. And if you are an outlier somewhere outside of that range, they know that maybe there might be something wrong, and they can kind of pick up on abnormalities that way. They can pick up on when you're way outside of that range of what we would consider to be normal. They may decide to do more tests or something like that. So that's why they do all those measurements when you go to the doctor's office. They actually chart your measurements on, if you look at my board here, this is a normal distribution, and this is what a graph of a normal distribution looks like, which we're going to talk about more in just a minute. But what they do is they chart those measurements that they take on you, and they say, okay, well, are they in the center of the graph? Are they within where most people lie, or are your measurements out here on the outskirts of the graph? Are you an outlier? Are you either way below or way above most measurements? And usually they will give your parents, if you're younger, percentages, and they'll say, okay, well, you're within 20, you're heavier than 20% of everybody else in your age group. And they can do that with height, weight, and everything else. And they give your parents percentages so that they can get an idea of where their child is in that what would be considered a range of normalcy, what's considered to be normal. And again, if there's an outlier, if your numbers are somewhere outside of that range of normal, then they might say, okay, well, we need to watch this. Maybe we need to do some more tests or something like that. So lots of real world applications to what we're going to learn about today. If you keep reading in the notes, it goes on to define what the empirical rule is. The empirical rule says the graph of a normal distribution is what we call a normal curve. Some people call it a bell curve because it has a bell shape centered on the mean. Here's a picture of a normal distribution. This is what we call a bell curve or a normal curve. And notice that it's centered on the mean. That means that the very center of your curve is your mean. All of your data is centered on your mean in a normal distribution. And then it says a certain percentage of all data values tend to fall in a certain interval of values ranging from the mean. And then it gives you in your notes something similar to what I already have on the board right here. This is a picture of a normal distribution. You've got your mean in the center. This +1 and -1 represent how many standard deviations away from the mean you are. So +1 means you are one standard deviation above the mean. A -1 means that you're one standard deviation below the mean, and so on. +2 and +3, these are the number of standard deviations above or below the mean. So you're either above the mean or you're below the mean if it's a minus. But that's what that +1, +2, +3, and -1, -2, -3 represent. It represents how many standard deviations above or below the mean you are. And you can tell by looking at the graph of this that most of the data is centered around the mean. And in fact, if you look at your graph, you will see that there are specific percentages written into the graph. You guys need to memorize these percentages, okay? I have not asked you guys to memorize a lot of things this year, and especially since we've started distance learning, I haven't really mentioned anything that you need to memorize. This is something that you need to memorize, okay? So make sure that you have a good picture of that bell curve and that you have these percentages because you are going to need to know them. So if this is your mean, you can see that within one standard deviation of the mean, whether you're above it or below it, it's 34% of your data on each side. So if you add those 34s together, that makes 68. 68% of your data is going to be within one standard deviation of your mean. If you go out to 2 standard deviations from your mean, you add another 13.5% in both directions. Okay? So if you wanted to know, okay, well, how much of my data is going to be within 2 standard deviations, you're going to add 34 and 34, and then 13.5 and 13.5. That's going to be the vast majority of your data. In fact, let's add that right now. So we know that 34 and 34 is 68. Let's add another 13.5 and another 13.5. And let's just see what we get. We get 95. So 95% of your data is going to lie within 2 standard deviations of your mean. 68% within 1 standard deviation, 95% within 2 standard deviations. That leaves that last 5% of your data is going to be from here, from 2 standard deviations below the mean or 2 standard deviations and up above the mean. That's going to be your last remaining 5% altogether. So you can see that the vast majority of your data in a normal distribution lies within 2 standard deviations. Anything outside of that we would consider an outlier. We would consider not normal. Okay? Okay, so I think that kind of covers the notes at least. For those of you, there may be some of you guys saying, okay, well, I see that this 2.35% here and 2.35% here, and that doesn't add up to 5%. The reason why that is because the 2.35% is what's going to lie within 3 standard deviations on each side. And then there's a little teeny bit left over because 2.35 and 2.35 adds to 4.7. There's still a little bit left over. That little bit left over is what's going to lie even outside of that. So that's going to be outside of the 3 standard deviations and outside of the 3 standard deviations this way. Okay? Okay, so now that we've kind of talked through the notes, let's kind of talk about the examples real quick also. This is where your book is going to come in handy because I'm trying to keep these videos to a maximum of 30 minutes. And in order for me to do that, you're going to have to help me out and follow along in your book because there's lots of graphs here to look at. And I'm not going to have time to graph every single thing with you if I'm trying to keep this to a certain amount of time. So together, let's look in our books at example 3 in section 8.3. That is on page 430. I am on page 430 right now in your textbook. And we're looking at section 8.3, example 3. It says, are the following variables likely to have a normal distribution? So it's giving you examples of different types of sets of data and asking you whether that is a type of data that would have a normal distribution. Part A says the heights of all the people in a large group. Well, remember we just talked about one of the typical types of data that has a normal distribution is types of human statistics like height, weight, chest circumference, head circumference, and things like that. So A, you're going to say yes, the heights of all the people in a large group, we would say is going to have a normal distribution to it. Part B says the probability of landing on each of 8 equal parts of a spinner. Well, the probability of landing on each of 8 equal parts of a spinner is going to have an equal probability of each thing. If they're equal parts and there's 8 of them, you're going to have an equal probability of landing on any of those 8 parts. That is not going to be a distribution that's going to look like this. That would be a distribution that's going to be a more even. Here, I'm going to go ahead and erase this. So if you're talking about data involved with spinning a spinner and finding the probability of it landing on any particular section, it has an equally likely chance of landing in any particular part of that spinner. So the distribution of data, that kind of data, is going to be very equal in value. You're going to have data that's going to be pretty much equal for each of those possibilities. So that is not going to be a normal distribution. Part C says the scores on an easy test. Well, if the test is easy, then you would expect the students to do well, right? So that might be something that might look more like this. This is how many. So this axis right here represents how they did on the test. So maybe you only had a few fail. And then if it's easy, then you would expect a lot of students to have high scores, to do well. So this is not a normal distribution, okay? Part D, the number of children in a family. Well, that's kind of the opposite. Most families only have 1, 2, 3, maybe 4 kids. So that distribution is going to look more like this. Most people don't have a whole bunch of kids. Most people have 1, 2, 3, or 4, which is going to be your data over here. And then as you have more kids, you're going to have less likelihood of people having 10, 11, 12 kids. So this is going to be a distribution that's going to look more like this. Okay? So just remember, normal distributions vary from the mean. Most of your data is going to be centered at your mean and very close to the mean. Okay? And it's going to have a symmetrical looking bell curve. It has to look like this. Okay? That is a normal distribution. It's where most of your data lies in the center, the middle of your data. Okay? Now let's flip back to section 8.4 where that's the lesson that we're actually doing today. And let's look at the explore and reason in section 8.4. It's actually very similar to what we've just been doing. It says the owner of an apple orchard and the owner of an orange grove create histograms to display fruit production data. So again, I'm expecting you to look in your book, okay? Look in your book. This is now page 435. We've now turned to page 435. And you can see on page 435, you have some more pictures. You have a histogram that shows apple orchard yield per tree, and a histogram that shows orange grove yield per tree. And if you look at those two graphs, you'll see that the numbers are completely different. The number of apples, numbers are way bigger than number of oranges. So the numbers are not the same. However, the distribution is the same. So both of those groves, the apple orchard and the orange grove, are both showing a normal distribution. But the numbers are different, okay? So part A says, describe the shape of each distribution. Each of them have a normal distribution. They are centered on their mean. Most of the values lie in the center of your graph or of your data. Discuss how the distributions are alike and how they're different. Well, they're alike because they're both normal. They're both normal distributions. Most of the data are centered around the middle of the data set. How are they different? Well, they're different because the numbers are different. So even the distribution is the same. The behavior of the data is the same. The actual data is different. Part B says, explain how you could estimate the mean from the graphs. Well, you can see from the graph that they have a normal distribution, which means that the mean is going to be right in the center. So if you want to find the mean for that data or for those graphs, find the middle. The middle is going to be where you can approximate what your mean is going to be. Okay, and then it says the standard deviation measures spread from the mean. Which data values are within a standard deviation of the mean on each graph? So again, you got to go back to that original bell curve that I had on the board at the very beginning. Remember that a bell curve has, that wasn't very good. It's cut down the center. So find the center. That's where your mean is. Okay? And then as you go out so many standard deviations from your mean. So if you look at that bar graph, you've got one bar that's in the center. Or you have a center data value. And then as you go out from that, you have bars that represent your standard deviations. Okay? So if it says which data values are within a standard deviation of the mean on each graph, those are going to be your three middle bars. The three in the middle are going to be your one standard deviation from the mean. Okay. All right, let's look at some, we've kind of really just been kind of discussing so far. We haven't really done a whole lot, like as far as figuring things out. So let's go to example 1. Next page over, this is page 436. Okay, page 436, example 1. Let's read it together. An example of an early application of statistics was in the year 1817. A study of chest circumference among a group of Scottish men exhibited an approximately normal distribution. Their chest circumferences ranged from 33 to 48 inches, with a mean chest measurement of 40 inches and a standard deviation of 2 inches. Use the empirical rule to help you understand the distribution of chest circumferences in the study. And part A says, what range of chest measurements contains the 68% which fall closest to the mean? Okay. So remember that within one standard deviation of the mean, whether you're going one standard deviation above it or one standard deviation below it, it's 34% of your data on each side. So this range from one standard deviation below your mean to one standard deviation above is going to be a total of 68% of your data altogether. Okay, so it says what range of chest measurements is going to contain that 68% which falls closest to the mean. This is the 68% that falls closest to the mean. It's what's within one standard deviation of your mean. So what we need to do is we need to put some actual numbers in here. So let's go back up. It says that the mean chest measurement was 40 inches. That's the number that's going to go right here in the center. Your mean chest measurement. That means the center number is 40 inches. The other piece of information you need is the standard deviation. It says the standard deviation was 2 inches. So if you want to go one standard deviation away from that mean, you need to add 2 inches and you need to subtract 2 inches. And that's going to tell you where you're at to be 1 standard deviation away from the mean. If your standard deviation is 2 inches, then you need to add 2 inches to go 1 standard deviation above the mean, subtract 2 inches to go 1 standard deviation below the mean. So anybody that is in the range of 38 inches to 42 inches is going to be within that 68% of the data, okay, within your mean, which was 40. 68% of the people studied are going to be between 38 and 42 inches, okay? How do we know that? Because we know that this data has a normal distribution, and if we know that it has a normal distribution, then we can make predictions because we know that there's a pattern to that data. Okay, so we're using the pattern that we know exists to be able to make predictions. Okay, so we know that 68% of our data will lie between 38 inches and 42 inches for chest circumference. Now let's go to part B. Part B says, what would you expect the chest measurements to be for the 2.5% of the men with the smallest chest measurements in the population? Okay, so it wants you to consider the 2.5% of men with the smallest chest measurements. So again, go back to your notes and look at your empirical rule and how that normal distribution is set up. We know that this is 13.5% within 2 standard deviations. And then we know that over here within 3 standard deviations is 2.35%, which is real close to 2.5. I think 2.35 is probably close enough to 2.5 that we could just kind of consider it to be basically the same. Okay, so let's go back to the question. What would you expect the chest measurements to be for the 2.5% of the men with the smallest chest measurements in the population? That's going to be, here I'll color it. That's going to be this part of our data right here. Here's your smallest 2.5% of your data, okay? These are our bigger chest circumferences. These are our, middle, average, normal chest circumferences. And these are our smaller chest circumferences. Our smallest 2.5% of our chest circumferences is going to be from here to the left. That's your smallest 2.5%. So we need to figure out what that number is going to be. Well, we know that the mean was 40, and we know that every time we go a standard deviation was 2. So every time we go a standard deviation away from the mean, we either have to add 2 or subtract 2. So if I'm at 40 and I want to go 1 standard deviation below the mean, I'm going to subtract 2. If I want to go 2 standard deviations below the mean, I need to subtract another 2. That's going to put me at 36 inches right here. That, from that point to the left, is going to be my smallest 2.5%. So that means that I would expect my smallest 2.5% to have chest circumferences of 36 inches or smaller. Okay, so let me write that down. So this is what we would say. The smallest 2.5% will be 36 inches or less. or smaller, you could say. Okay, so it's really just a number line, guys. You're putting the mean in the middle, figure out what the standard deviation is, and then either add it or subtract it depending on whether you're going below or above. Every time you add or subtract it, you're one standard deviation away from that mean. Okay. Let's look at example 2 also. Example 2 says recent SAT scores for college-bound seniors are normally distributed with the mean score at 508 and a standard deviation of 121. How does the empirical rule help you understand the performances of individual students? Part A says what proportion of students received scores between 387 and 629. So you need to do the same thing here for that you did here, okay? You need to make a new number line. So I'm going to erase this. And we're going to create a new number line now with new numbers. It's going to work the same way, it's just that the numbers will be different now. So we're now on page 437. And we're looking at example 2. Draw a new number line, new normal curve. Okay? All right, recent SAT scores are normally distributed. Here's our normal curve showing our normal distribution. The mean score is 508. That's your center. Mean is 508, right in the center. And a standard deviation of 121. So if I want to go one standard deviation above and below the mean, I'm going to add 121 and I'm going to subtract 121. Let's take our calculator. Let's do 508 plus 121 is 629. That puts me one standard deviation above the mean. That's 34% of my data right there. Now let's take that 508 and let's subtract 121. 387. That is your one standard deviation below the mean. That's another 34% of your data. I think we can actually stop right there and answer the question. Let's go back to the question. What proportion of students receive scores between 387, that's here, and 629, that's here? So 387 and 629 are the data values that are within one standard deviation of the mean. So that's going to be 34% in one direction of your data, 34% in the other direction of your data. Add those percentages up and you're going to get 68%. So we would expect 68% of the students to score between 387 and 629 on that test. Okay? Those are the scores that are within one standard deviation of the mean. So that's going to be 68% of your data. That's part A. Okay, let's go to part B. Part B says what proportion of students receive scores greater than 387? What proportion of students receive scores greater than 387? So greater than 387 would be this part of my graph right here. It would be everything from here over. Okay? I want to know what percentage of the data values that is, or what percentage of the graph that is. So there's probably a couple ways to figure that out, but here's what makes sense to me. Here's how I would do it. I would say, okay, well 508 is my mean. This cuts your graph in half right here at the mean. So half of your data is going to be from the mean to the right, above the mean. Half of your data is going to be above the mean, half of your data is going to be below the mean. So I know that 50% of my data is here. If I want the percentage of the data from here over, I know this half is 50%. Now just add this little section right here, which is 34%. That's going to give you 84%. Let me go back over that. So the question was, what proportion of students received scores greater than 387? Well, 387 is minus 1 standard deviation below the mean. Okay? I want to know what percentage of the students scored above that. So in other words, what percentage of my students are from here over? So I know that from the mean over is half of the data. That's 50% right there. Then we just needed to add this little section right here, which is just the 1 standard deviation below the mean, which is 34% of your data. So 84% of your data is going to be from here bigger. Okay, 1 standard deviation below the mean up is 84% of your data. So I hope that you're beginning to see now why I told you at the beginning of the lesson that you need to memorize these percentages. You have to know them, and they're set. They don't change. Those percentages stay the same every time if your data is normally distributed. If it's normally distributed, it has a predictable pattern to it, and that is the predictable pattern, is those percentages. So the percentages are going to be the same every single time if it's normally distributed. So yes, you need to memorize those percentages, and you need to be able to use them. Okay. Hopefully I've kept this to 30 minutes. I'm not real sure, but I've tried. Again, if you still have questions, still not sure about things, if you're trying the homework or the assignment that goes with this and you're having some difficulties, email me, let me know. I can make another little help video if I need to. But hopefully this at least will get you started, get you an idea of what you need to do and how to do it. Okay, I will talk to you guys later.